And with that, I don't think that I forgot anything. I will pass it over to one of the co-leads, Wilbert Wire, to introduce the meeting today.
Great. Thanks, Hazel. So welcome to this session of IARPIC's Modelers Community of Practice. For anyone who is not familiar with IARPIC, it is the Interagency Arctic Research Policy Committee, which brings together leaders from 18 agencies, departments, and offices from across the U.S. federal government to enhance collaboration on research in the Arctic. Today's session is being hosted through IARPIC Collaborations, which is a platform that connects federal government researchers, non-federal researchers, and Arctic communities to work together on pressing Arctic research issues. The Modelers Community of Practice aims to enhance understanding of the integrated Arctic system through the use of regional and global Earth system models, primarily through the organization of monthly webinars like these. The co-leads include myself, Rino Joseph, Hannah Mavenkamp, and Lauren Andrews. Today, the session will be about discrete element modeling of sea ice. I'm not going to discuss that. I'm pretty sure that Adrian or Georgy will convince us about the relevance and the importance of that. So we have two distinguished scientists, Adrian Turner and Georgy Manucharyan from the University of Washington, who will discuss their experiences in developing discrete element models for sea ice. So we start with Georgy Manucharyan. He's an associate professor at the University of Washington. He has a PhD in climate dynamics from Yale University 2014, and he will talk about the sub-zero sea ice model. So take it away, Georgy.
Mm-hmm. Thank you. Thank you for inviting me. All right, so I'll talk a little bit about this project, Sub-Zero, and it started off right before the COVID started, I guess. And I started my position as a professor at the University of Washington, and one of the postdocs there, Brandon Montemuro, was a really key developer, and since then he went to St. Michael's College, but he still is involved. And thank you also to ONR and NSF for funding this project. So just a very, very brief introduction, which I'm sure you're all familiar with, but the idea is that if you look at close and close scales on sea ice, you start resolving features from very large scale dynamics. As you can see, things look blurry over here from satellite images of sea ice concentration. But if you zoom in to start looking at sea ice at 1,000-kilometer scales, you see all these leads and fractures opening up, and then you go even closer. At say 100-kilometer scale, you see this little fragmented pieces of ice. And I'm sure there's like many more images. You can go down to scales of centimeters or millimeters, depending on like what exactly you're trying to study. But the idea behind Sub-Zero was to create a model that can allow us to represent this kind of fragmented nature of ice. So just a very brief introduction of what existing models were at the time. This has evolved, but before I started designing Sub-Zero, I kind of drew inspiration from some of these past studies. And discrete element models of sea ice typically composed of some type of elements. They could be point elements represented by disks or spheres, and or polygons, like in this case, squares or something like that, rectangulars. But the idea is that you will have a whole bunch of elements, and you would prescribe sort of bonds between those two elements, and those bonds will be something that would tell you what the forces are acting on these elements. And then you'll subject the whole system to external forces and try to figure out dynamics of each individual element, subject to also some fracture criteria to those bonds, usually based on some sort of critical stresses, or you can have maybe a bit more sophisticated model of stress for those bonds. And these models are very powerful, and they can they look, when you zoom in, they look a little bit strange. Doesn't look like sea ice, but given a huge number of those elements and correct equations that you prescribe for interaction laws of those, these models can become very powerful at simulating the large scale motion of sea ice, as well as the formation of fractures. So what we were looking at when it came to Sub-Zero, we looked at trying to basically provide a sort of alternative formulation to those models, and maybe not so alternative, but a little bit different, such that you have, as part of your dynamics in your model, you have these chunks available as a state of your model, rather than having CIs being sort of composed of tiny little interconnected pieces, elements, and then deduce what the flows are in those based on available connections. Instead, you just have flows everywhere, and those flows should naturally kind of crush and experience some sort of physical processes similar to what you might see in observations, right? So one flow, for example, could be crushed by forces from surrounding ice and split into multiple flows. And this is what basically motivated the development of the Sub-Zero model. So behind its dynamical core, it's pretty similar to what our previous models have, with only with the idea that you would have an element. In this case, we're using polygons, and it has mass and center location, and it can accelerate subject to all the forces acting on it, from atmosphere and the ocean, from collisions, and from some parameterized unresolved forces. These flows can also rotate around, so we're talking about 2D motion of these flows. And for the purpose of Sub-Zero, we need to make sure that these flows could be of arbitrary shapes. So they cannot just be circles, because we want to split circles into half if you fracture it, or in multiple pieces. And then we can also merge them subject to thermodynamics. So as a result of running this model, you can end up having a whole bunch of different shapes. And that means collisions become very complicated, because you can have multiple collision points between two concave polygons. And for computational reasons, how you resolve those collisions, you allow some sort of overlap between the two. So if you zoom in over here, there is a tiny bit of overlap between the two shapes of those polygons. And you can make it as small as you want, depending on how big your computer is. But you still need an overlap to determine the direction and the strengths of forces acting on the flows. So once you do that, you can basically collide the two polygons, and they will behave subject to the rules of collisions that you prescribe. And going into sort of more advanced processes that this model simulate is, you can, of course, try to weld the elements together, right? So in conventional DM approach, you would maybe create bonds to connect the two chunks of ice together. In this case, you just have a new chunk of ice, which is welded together, and this is a new weirdly shaped polygon, right? You can have similar parameterizations for regional rafting, and you can have, importantly, a flow fracture criteria, where you say, well, if the stresses that this flow experiences are large enough, then you can fracture it into multiple pieces, right? So this is where the two flows collided, and let's say this flow was big and strong. It didn't experience as strong of stresses internally, but this one fractured, and you can prescribe some sort of stochastic process that would fracture this flow into pieces, and now you have more elements in your model. So this is basically, at this point, I'm not, since there's not a lot of time, I'm not going to go into too much detail, but just to say that it's an absolute pain to model this, and there are just so many bad things that happen with all these flow geometry interactions, and with memory issues and all of that. And together with Brandon, we managed to have a version that is working. So if you try to do it at home, you're in for some some trouble, but it works nonetheless at this point. So and I'm going to show you a couple of examples of how this model can be used to study sea ice. So one example here is where you would try to figure out how flows propagate through Nares Strait. So Nares Strait is this region. This is Greenland over here, and a lot of sea ice is escaping through the strait. But throughout the winter, the ice motion there is shut down because of ice bridges that are forming, and then around summer, at some point, the ice becomes thinner and weaker, and it fractures, and the flows propagate through. And this is a cool example to study because hold on, because you can only observe fractures because the fracture processes are happening very rapidly over the course of like a couple of days. Everything gets fractured and flows go through. So we can ignore quite a lot of thermodynamic processes happening there and just use this experiment as a test bed to understand just the collisional and fracture behavior of sea ice in this model and basically fine tune it based off observations. On the right here, I'm showing two quantitative metrics. One is the area fluxes that are measured over here from satellite analysis of real observations. This is the solid blue curve over here. And a couple of simulations where we fine-tune parameterizations of fractures. And we start recovering this dynamics over here, this statistical behavior of area fluxes, which have a little bit of a long tail over here. And this long tail is associated with jamming events. This is basically saying that a lot of times you can have zero area flux. That's because this granular type media can just basically jam and not move until enough flows experiences a buildup of stresses and collapse, and then everything just goes through. So you will jump from zero flux to a lot of fluxes. So it's a bit of a non-Gaussian distribution. And another thing over here to mention is that the model itself, since it has flows as elements of various sizes, you can diagnose quite quickly the flow size distribution and explore the properties of it. So over here, we also done a satellite analysis of flow size distribution and looked at how model is capable of simulating it. And by basically fiddling with parameterization of fractures, we realized that we can make actually inferences of how flows fracture if we want both of these quantities to be satisfied, meaning the model to simulate reality as close as possible. Then we can make inferences on what types of parameterizations are more appropriate and in this case, we found that, for example, the critical stress that a flow can experience before fracturing is basically proportional to its length scale to a square root power. Well, minus 1/2 power, 1 over square root power. So another application is an application to wintertime equilibration, right? So this is where you have an absolute nightmare because all the processes acting together, you have chunks of ice fracturing, you have chunks of ice welding together, and they're growing thermodynamically. So all their strength characteristics are changing, the thicknesses are changing. And at the end of it, you can say, well, is this model going to equilibrate to anything, or it's going to just blow up and you're going to have nothing? Well, turns out you can start this model from a very unrealistic distribution, like a delta function distribution of ice thicknesses, meaning you start the whole simulation with uniformly covered sea ice. And then after a couple of weeks, what you see is the evolution of the ice thickness distribution that ends up looking a lot like observations. And in observations, there is some sort of mean ice thickness, and it looks like not really a Gaussian, but some sort of slanted Gaussian, or like asymmetric Gaussian. And people had theoretical studies modeling this as a gamma distribution, and specifying, reasons why it should be gamma distribution. But in any case, the model is approaching to mimic the ice thickness distribution as well as flow size distribution. I'm not showing it here, but the flow size distribution is also matching characteristic range of power laws that we observe there. Now, another application that we're working on, this is currently in development, which is to figure out how good this is in, Sub-Zero is in fracturing and creating this sort of elongated linear kinematic features or leads. And this is now coming back a little bit to the ideas of conventional discrete element models, which use bonded bonded particle method. So Sub-Zero basically can be reconfigured to be reduced down to a conventional DM, where each individual pieces stay coherent in time. They don't change their shapes, but the bonds can be created or fractured. And over here, this formation of sort of an idealized uniaxial compression, formation of leads in an idealized uniaxial compression experiment is basically a test bed to see if everything runs well. And looks like it's doing what it's supposed to do at appropriate angles, roughly speaking, over here that you're supposed to have, given the roles that we prescribed. And then we proceeded to say, explore the collapse again in the Nair Strait. So this is a Nair Strait sea ice. So now ice is technically propagating here from a right to left. And this is the pre-collapse of the arches, or like this is how the ice arches collapse. Arches over here and another one over here on both sides of the image. But what you see here is that right before the complete and sort of shattering of sea ice, you see from the satellite image quite a lot of fractures forming. And these fractures are kind of connecting a bunch of points related to the island, and maybe some of the points here related to certain coastline features. Of course, there are some intermediately leads in the interior that also appear, but one can hypothesize that these islands play a huge role in as sort of stress concentrators or providing weakness points where ice can break. And we've tested this idea with this bonded element version of Sub-Zero. And this basically fractures should occur really rapidly, but I'm just slowing it down for you. And you see that the islands actually do play quite a big role, because all these fractures tend to originate around these islands, and they tend to connect the island points to some of the coastline points where the geometry perhaps causes some stress localization. Like these two fractures, they will eventually find each other. So because the time is very limited, I'm just gonna leave it at those couple of examples and have you guys ask questions. But the state of the model at this time is that basically we have a model, it's written in MATLAB, but since then we have a version of it that is in Julia. And really the version that's in Julia is meant to be coupled with this MIT GCM version of that is written of Ocean Model that is written in Julia as well. It's called Oceananigans, and to study sort of idealized ice-ocean interaction processes. But if you are interested in just the ice mechanics, you can run this model and explore processes that control flow size distribution or ice thickness distribution or the formation of leads, and try to really nail down the processes of that control either material properties of individual chunks of ice or the collision rules. And if you have a lot of observations that can inform the behavior of model, even observations of large-scale quantities like area fluxes, or if you have ice thickness distribution or flow size distribution, that's even better. You can constrain quite a lot of interior physics of the model. So here are some references for you. And there are more people publishing papers usually using the sub-zero models, but this is just to point out the original one, so written together with Brandon over here. And then there's a Journal of open source software where you can download the code and find some references and see if you can use it for anything good. And more physics will come out. So this study over here, which is more of a scientific study, which says explores the role of islands and really demonstrates the utility of this model, is I just point out as one of the cool ones. All right, thank you so much. Hope I didn't take too much time.
No, this was perfect. Thank you, Georgy. How about a couple of questions before we hand it over to Adrian? Let me know. Please raise your hand if you have a question. Mike.
Could you say once you have this, which looks fascinating, how do you go about getting the fluxes through these various ice elements and the evaporation, and then is there atmospheric interaction over these elements between the leads and the ice flows?
Yeah, so at the moment great question. So at the moment we've been focusing on ice mechanics of fractures, and then there's a thermodynamic component which is fairly primitive. So it's more like if you have atmosphere, so the model itself, it just takes whatever flux that you give it from the ocean and from the atmospheric model, and then it's up to you to specify the parameterization of what you have. What we've done as a very simple one. So you have ocean model under each of these elements, and you basically interpolate the ocean state onto the location of where the element is. So now you have effective temperature of the ocean and temperature of the atmosphere over each individual ice flow, and you can prescribe some sort of bulk flux parameterization for what would be the heat flux, and then you can grow it up and down the ice flow. And from mechanical interactions, the ice can be strengthened. If it's thicker, it gets stronger, meaning it can withhold more stress. And then also under cooling conditions where you think that you want to grow ice, what happens is that if you create some areas where there's open water, you can now populate this area with new elements if you're under the conditions that freezing is expected to going on. So you'll create more elements.
Well, if I could ask one more thing, have you compared results of the flows that occur when you do it this way as opposed to the previous way with sort of larger flows or more generous ones, or does it make a difference, I guess, is the question.
Yeah, so this is to be determined, right? So I would say that for large scale quantities, right? If you're interested in just simulating, let's say at hundreds of kilometers scales, what's going to be the flux of ice, right? If you're interested in this bulk characteristics, then you can tune whatever model you have. You can even tune continuous PDE model, right? Let's say Hibbeler's model to represent you the bulk quantities. So this model you would use when you're interested in really flow scale things, really like tiny chunks interacting, and you're interested, well, how the flows break, how the leads form, and in a you can also, I guess, set up comparison if we all agree on some sort of metrics of significance, then we can try to simulate those metrics with various types of approaches, right? And when the Sub-Zero was developed, really my main I guess I don't know concern with existing DMs was that it would be hard for them to simulate a wide range of FSD or flow sizes for the FSD. because the conventional approach is that you populate everything with flows and they're interconnected, and now you start crushing them, but it's very hard to get, say, 3 or 4 orders of magnitude difference between the sizes of flows that you have, and have a lot of these flows. In this model, you can just basically have any size ratio that you want. You can have one element this big and right next to it like an element this big, because I've simply initialized the model, or I simply crushed the model, and that would be the range of resolved flows in my model. So it's a bit more natural. So maybe that would be one advantage where you can say use this one instead of the conventional one. But yeah, I would say time will tell if this has a big utility over the other ones.
Very interesting. Yeah, I mean, does ice form faster in the fall, or melt faster in the spring, or anything with this?
Oh, it would depend on yeah, I guess it would depend on the context, right? So we'd need to do a seasonal cycle simulation of some idealized square
Yeah.
basin, and tell you. But this is really, I would say, if you're interested in large scale behavior like seasonal cycles of bulk quantities, maybe you're better off with using some simple model, and the whole devil will be hidden in how you prescribe the fluxes from the ocean and from the atmosphere to your ice. Like it's all going to be sensitive to this flux parameterizations rather than mechanics of ice. This is more like advanced model for sea ice mechanics.
Oh, thank you. Yeah.
Mhm. Thank you for the questions.
All right, excellent. Thank you. If you have more questions for Georgy, feel free to put them in the chat. So now we're going to hand it over to Adrian. Adrian Turner is a staff scientist at Los Alamos National Laboratory. He has a PhD in astrophysics from the University of Cambridge in 2004, and he's going to talk about the discrete element model for sea ice, DEMSI.
Thank you, Robert. Thank you for that introduction. Yeah, so I'm going to talk about a joint Los Alamos and Sandia National Laboratories project called DEMSI, the Discrete Element Model for Sea Ice. The project has myself and Carolyn Begerman from Los Alamos as part of it, and Kara Peterson, Svislov Nikolov, and Devin O'Connor from Sandia. Yeah. Okay, so the goals of the project have been to explore the challenges that there are to develop a general sea ice model based on the discrete element method. Originally, the project was looking at global long-term simulations, but more recently has been more focused on shorter term and regional process simulations. So our view is that the discrete element method sea ice model has some potential advantages, two of which would be hopefully it would have a better improved fidelity of sea ice dynamics, and has an advantage of being able to include explicit representations of fracture and flow bonding, and also that this would be an opportunity to better utilize the GPU supercomputers that the DOE is increasingly what DOE uses for computation. Okay, so we heard about the DM method, so I'll just briefly describe it here. So we have Lagrangian particles, which traditionally has been used for modeling granular materials. In the method, you explicitly calculate forces between those elements when they come into contact. And then based on those forces, as well as any other body forces, the elements feel the equations of motion for the individual elements are integrated and the position of the elements updated. It's traditionally been used, this discrete element method has traditionally been used for industrial and geomechanical applications, looking at grain materials like soils and things like that. And as we've heard, it's also been used for sea ice. So in terms of actually developing a discrete element model for general use in sea ice modeling, there are a number of challenges that this project aimed to explore. First was how to represent sea ice consistently with these elements. What kind of element contact model would be suitable for sea ice? How to represent ridging and deformation of sea ice in these models, something that most discrete element models in other application areas don't have to contend with. And also then how to represent fresnel formation and the creation of new elements, which is necessary if you want to do longer term simulations with the model. So just give it an overview of Dempsey. It consists of two independent dynamical cores, a basic one written in C++ that's used for rapid prototyping and physics development, and then a higher performance dynamical core that uses the Sandia LAMMPS model, which is a molecular dynamics model that has built-in discrete element capability, as well as the ability to use COCOS to give the model GPU portability for the dynamics. And then column physics is provided by the IcePack column physics library provided by the CICE consortium. And this is the column physics that's also used in Lanol's CICE model and MPAS-CICE and E3SM, the DOE climate model. So one of the challenging areas is how to represent ridging and deformation. So ridging results in deformation of sea ice, and as so we model this in the model by representing it as a friction. So when two elements are converging together, they begin to overlap, and this overlapping generates a repulsive force. Beyond a certain limit, that force is limited by a friction limit, and beyond that friction limit, since the force is fixed, the elements continue to move together. So that's how the ridging is modeled from a forces point of view. But after the overlap, in terms of geometry change of the elements, I should say we model things using circular elements and ellipsoid elements rather than polygonal elements. So with the geometry change, we start off with circular elements, and then the ridging is represented as a transformation of the element shape into elements, as you can see in the sort of diagrammatically in this figure in the bottom right corner. And the deformation to ellipses is important because it preserves the directionality of the ridging. If you just shrunk the elements to represent the lossing sea ice area during ridging, then you would lose that directionality. So our element shape are ellipses, but ellipses are very computationally taxing to find contact detection for them. The very minimum you need to do is to solve a quadratic equation for each pair of overlapping ellipses. I'm not going to go through these diagrams too much here, but this is essentially the method that you need per contact to calculate the overlap. You need to do a mapping into a space where one of the elements is a unit circle and the other is aligned with the origin, and then do a root finding on a particular function that comes out of that mapping, and then map back to real space. So it's very computationally expensive to find that contact overlap, which is needed to calculate the forces between elements. So we have developed an alternative to this, a hybrid method where the elements remain elliptical, but rather than calculating that overlap, forces are still calculated on the element center line, which is very cheap to calculate the distance between ellipses along the center line. And we include an additional torque based on the angle between the ellipses. And we find not only do we have a significant speed up in this methodology versus using the full ellipse formulation, but we also end up with no significant difference in the output of the model. So this ridging formulation for elements has been validated in both one-dimensional test cases, which you see on the left here, comparing basically have thickness and velocity in one dimension along a region with winds blowing to the right, and a comparison between emperor sea ice and Dempsey. You can see the ice building up along the shoreline on this eastern side, right-hand side, and a relatively good comparison between the two models. And then in this test case here on the right, where we have winds blowing along a 90-degree shoreline, you can see the formation of ellipse-shaped elements through the ridging and the thickening of them, thickening of the ice as they undergo ridging, and there's really no difference between the two methods. The other thing included in the model is fracture. So elements can be frozen together and then undergo fracture. We use the bonded particle model, which is a discrete element method bonding model that's had a lot of success. There's a picture of results from a uniaxial compression using that model in the right-hand side, and you can see the generation of conjugate faulting. So the model has a piece of cement between the two elements, and the piece of cement undergoes forces as the elements move, and once those stresses in that cement exceed a limit, then the cement breaks. And for sea ice, we include the ability for the cement to return through a healing process should simulate healing of damage between sea ice through freezing of ice. Oh, what's happened here? Oh, well, this is inconvenient. Hang on a sec. Let me stop sharing if I can figure this out. Right. Sorry about that. Computers, eh? Well, I'll just do it here in PowerPoint. Hopefully you can see this. So the fracture and healing, we've validated this in a number of idealized test cases, sort of shown here. An example of the uniaxial test case where a sample is compressed from above, and you see the conjugate faulting developing in the model. We've explored this in uniform stress test cases where the sea ice breaks up into floes, and also in standard test cases where winds blow the sea ice onto islands, and you see shear here forming bands. A comparison between the EVP, rheology, and impasse sea ice here, and the fracturing in Dempsey. One of the issues with ridging is that over time elements become smaller and smaller as the area gets converted into thickness through ridging. Over time, this is going to necessitate shorter and shorter time steps, and the distortion is a problem that needs to be ameliorated. One solution is that periodically the model maps particle distribution back to an initial clean initial distribution consisting of the initial particle distribution the element started with. So this is remapped conservatively and using a linear representation of the traces within each element, relatively low numerical diffusion. Basically, each particle carries its original Voronoi polygon that was created at the start of the simulation, and then that geometry of that is used to map the traces back to the initial particle distribution. One problem with that, though, is that when you do that, you end up with CI's concentrations greater than 0 if multiple of these polygons overlap. And so we also use a global optimization using PermQP, which is a quadratic program that we use to optimize the solution to bring elements back into a concentration between 0 and 1. Final kind of challenge that we've looked at is frazzle ice formation. So again, for longer term simulations, we need to create new sea ice from the ocean. We need to thicken elements where they already exist, and then create new elements where there are no elements. The real challenge here is one of computational geometry. We want those new elements to be tightly packed so there aren't any gaps. And you kind of see this diagrammatically on the right, where we have initial particles and some frazzle coming from the ocean, an ocean model beneath the sea ice model. And so the blue elements represent ones that where elements already existed, and so we just want to thicken those pre-existing elements. We also want to create new elements where there weren't already existing ones. So two options have been explored to do this. One using the global particle remapping we just described previously as an opportunity to create new elements. This works really great. We get a really tight packing of new elements because the initial distribution of elements is tightly packed, but this update happens infrequently. Or we can spawn new initial elements. But the problem with this is that when you do this, you can do this as often as you want, but you end up with gaps around existing elements. So, like I say, this is a problem of computational geometry, and we are exploring potential algorithms to create more tightly packed distributions on the fly. So just to conclude, simulating sea ice in a general sea ice model with a discrete element method has several significant challenges. Through the Dempsey project, we've explored some of these challenges with some success, but still further work needs to be done for a general discrete element sea ice model. In terms of future work, working now on validating the model with longer term simulations, both basin scale simulations, as well as more process studies in the Narrow Strait and other places in the Canadian archipelago. Developing machine learning methods to help assess the fidelity of the patterns of deformation we get with the model, as well as looking at using Dempsey to train graph neural network emulators. Okay, and I will stop there.
Great, thanks very much, Adrian. Please raise your hand if you have a question for Adrian. And if you have any leftover questions for Georgy, then feel free to speak up as well.
There is one question in the chat from Laura and Decker. I don't know if that got answered. Is Lauren still on? Yeah, she is.
Yeah, is that if it's a question for me and Sub-Zero? Yes, we are playing around with land-fast ice, having some sort of different characteristics from the interior of the ice. And yeah, it does break up, but we need a better model to constrain it. So we've been using to constrain the difference between what we call mechanically how strong the land-fast ice is, how well it's attached to the coast and things like that. So there's a whole bunch of parameters that we can put in. And yes, if you force things strong enough, you can have like a chunk of land-fast ice stay and then the ice next to it go through. Or if you force it and even strongly, you can have land-fast ice break away completely too. So the devil is in a whole range of parameterizations that we're using and that do need to be constrained with observations somehow.
I can ask the next question too, is basically when you're looking at like some of this landfast ice breaking off, that always makes for interesting sort of, near shore polynya events. But also just looking, both of these models seems like they would be very good at identifying very early polynya opening in like, the north end of Baffin Bay. And so I was just wondering what kind of scale both of you would be thinking about. What's the biggest scale that you would want to operate this in? Because this seems very computationally heavy.
Yeah,
Adrian, you go first.
sure, okay, yeah. For Dempsey, like I say, your original application was global scale simulations. Yeah, so obviously there your elements are relatively big, and in that case we had a nice thickness distribution per element. So they really represented kind of regions of sea ice rather than individual small scale flows. Increasingly, we're looking at a much smaller scale. So yeah.
And in our case, it was original application was just idealized studies. So we were thinking about scales of like hundreds of kilometers, like a few hundred kilometers and smaller. And it was really just to understand fracture processes rather than doing climate scale simulations. But then now that we understood that the utility of this model, there's been a lot of discussion of how to scale it. And one way that we thought would be interesting is to use existing climate model sort of sea ice representations, but embed in regions of interest this high resolution discrete element model. And we've experimented with how to do it, and basically you would need to split to get the sort of large scale deformation fields from, or maybe stress fields as boundary conditions for your discrete element model, and then have a more high resolution coastline and just try to come up with some sort of interactive schemes between these two models. So played with it. It sounds very promising, but we haven't implemented. But that would be our vision of how it could be used, say, for climate scale simulations, where these models are extremely computationally heavy, and also climate community already have very heavy atmospheric and oceanic models, and they really don't like an even heavier ice model. So, but if you just say, hey, like I'm interested in, for example, fixing the transport through Nares Strait, and within this region I want a more detailed model, I think that would be a proper way forward, at least for our model. Yeah.
Before handing it over back to Mike, just a follow-up question on this. It seems like both of your methods are really good at interacting with topography, but do they also take care of bathymetry? Do they allow interaction of the flows with bathymetry?
Yep, they could do. Dempsey doesn't at the moment, but it certainly could.
We have stumbled upon this problem when we simulated lake ice, and we realized, okay, in a lot of area, it's like under 1 meter, so deep. And I mean, we can put something in it. That's the thing. Whatever you guys want, we can put some representation of forces on the elements, but they're only as good as that parameterization is, right? So we need to have some sort of constraints on the physics of what's going on, right? So you can put some friction, or you can put some weaknesses with surrounding ice flows. I would say more observations are welcome to develop some parameterizations for these types of models. And there are many processes, including waves and a whole bunch of things that we didn't do yet.
Great, thank you. And Mike?
So this is a question looking ahead a good bit, but maybe it'll be useful. So I was on the synthesis team for the first Arctic assessment, and one of the messages from the indigenous participants in that was that climate is changing. It was changing in a way so they couldn't predict the weather. And what it turned out they meant by that was that all the empirical information they had gained over the years about practices was now being sort of invalidated by what climate change was doing. And so I guess I'm wondering if you might go back in time and sort of do some cases of not present sea ice, but past sea ice when ice was thicker and different, and see if you can get a sense of if things were different and how they were different. And in that way sort of help perhaps test out or validate empirical wisdom that they had. I mean, one of the problems that was starting to occur, and I think it still occurred, is ice was breaking away from land, is now breaking away from land more rapidly and differently than it had in the past, and fishermen are getting sort of isolated out on these ice floes that break off, and they're having to be rescued and stuff. So it would be interesting to have a sense over time of how the conditions and the dominant processes have perhaps sort of changed, given that you now have a good bit thinner ice and things. So this might be an interesting kind of area to go.
Okay, thanks.
I agree.
All right, any more questions? All right, if not, then maybe we should thank our speakers again. Thank you, Adrian, and thank you, Georgy.
Thank you.
So our next meeting is going to be on May 18th. It's going to be on a Monday, so a different time for us. Modeling ecosystem disturbances, with presentations by Nancy Fresco and Ken Tape. So with that, I'm handing it back over to Hazel to close off the session.
Yes, thank you, everyone. I should have been ready with the link to that meeting page, and here I have it now, I think. So hope to see you then, and thanks for joining. And again, the recording will be posted probably this week or next week. So if you have folks who were not able to join today, feel free to pass that along. And good to see you all as always, and we'll see you next time.
All right.
Thanks
Thank you.
a lot.
Bye-bye, everybody.